Recording in progress.
All right, my seat's in the way. Okay, there we go. All right, so good afternoon. Hope everybody's doing well. Let's see. It's gonna bother me. A second. Sorry, the lighting was gonna bother me. All right, so first things first. So we are at, what is this, problem 11? Yep, problem 11. So we did part A, and we're on part B. So what we need to do is, this is for water, first of all, and kind of look up at the previous page. You'll see there's a couple of things that we said we needed to find. We need to find the phase. We need to find a, I think PV diagram was listed first. And then we also need PV diagram. So this is an example of, I actually put too much information on here, but it's fine. It is what it is. And I'll show you what I mean in just a second. So we've got water, 10 bar, 150 degrees Celsius. And the first thing that you want to do when you're figuring out the phase of something is to go to your saturated tables, not because you are assuming that it's saturated, but because you're going to use the information there to tell you what phase it's in. So I've got table A2 and A3, both are saturated water tables. One's organized by temperature, A2, one's organized by pressure, A3. And so let's see, so table A2 organized by temperature, I go to 150 degrees Celsius. I can see that, well, if it's saturated, my temperature or my pressure has got to be at 4.758 bar. So you can see I'm at 10 bar, of course. So my pressure is greater than E sat at T at 150 degrees Celsius. And then you could also, I mean, I'm done here, right? I mean, at this point, I've kind of figured out what I need to figure out. So I could say, well, it's compressed. By those rules that I've got, it's compressed. So I've answered the first thing, but I could also use the information in table A3 to get there. So I could go to 10 bar and see, well, if it were going to be saturated, my temperature would have to be 179.9 degrees Celsius. So in other words, my temperature is less than the Tsat at P. So that's another thing that would tell me that it's compressed. So what I want you to do is put an X through this. Not only do we not need it, but also it's a little snippet from the superheated tables just to add some extra confusion in there. So yeah, I tried to add some extra stuff to our notes to make it easier to progress through, but clearly I was in a hurry at this point. So just ignore that. So part 2 for this problem is we need to draw things on a PV diagram, and we're going to actually go through and I'm going to show you how we can use lines of constant pressure and lines of constant temperature to show us or to prove, I guess, that yes, in fact, we are compressed in this case, or vice versa. It's superheated. We could show we are superheated. All right, so we know that I'm going to go ahead and put a mark out here in. Oh, and I'm so sorry, I did it again. These lines should be. Actually, no, I did. That was right. That was right. This is a line of constant temperature. Yeah. So all along this temperature. Anywhere along that dotted line, the temperature is 150 degrees Celsius. And we are right there. So right there in the compressed liquid region. Now, if I wanted to, let's say I wanted to know what this pressure was, well, this is just, that pressure would be the saturation pressure at 150 degrees Celsius, or based on the information in table A2, it's 4.758 bar. So I'm going to go ahead and put that here. So 4.758 bar. So you can see that, that does make sense, right? It's below 10. You can see that makes sense there. All right, so let's draw things on a TV diagram. There, see if I can't things. All right, so we are at 150 degrees Celsius, and if I wanted to put, actually, it's compressed, isn't it? Anywhere along this line right here, our pressure would be 10 bar. So this is our state right there in the compressed liquid region. Oh, shoot. Nope. Apologies. Got ahead of myself here. Draw my line of constant pressure first. So anywhere along this line right here, our pressure is at 10 bar. Apologies. And so my dot would be right there. All right, so we'll say that's 150 degrees Celsius. And if I wanted to know what this temperature right here is, well, this would be the saturation temperature. That would be Tsat at, it's a little bit smaller, Tsat at 10 bar, which if you look over here at table A3, you can see that's 179.9. So let's write that down here. So 179.9 degrees Celsius. So you can see it, it makes sense, right? As far as where it is on the y-axis there. Okay. So let's go on to the next guy. All right, so this one, I didn't really have to change it because we're not pulling property data off. But I added some stuff here because I had a sort of a panicky moment when I looked at it the other day, but actually I really don't need any of this stuff. So I'm going to cross this stuff out. The only thing you need to answer this problem is A2 and A3. So I had changed it to 0.7 bar. It really honestly doesn't matter for what this problem was asking us. But let's go ahead and go with 0.7 bar. And yeah. So the first thing I need to do is at 0.7 bar and 100 degrees Celsius, what phase is our substance in? So for that, I'm going to table A2 and A3 are saturated tables, and just using the information there to tell what phase it's in. So for table A2, that's organized by temperature. And so I could see at 100 degrees Celsius, the pressure that we would have to be at and be saturated is 1.014 bar. So we're at 0.7 bar. So our pressure is less than Psat at 100 degrees Celsius, which means that it's superheated by the rules that are on that page, a couple of pages up. But we could also look in table A3, right? So at 0.7 bar, you'd see if it's going to be saturated, our temperature would have to be 89.95 degrees Celsius. If it's not, then it's not saturated. So in this case, our temperature is 100 degrees, and so our temperature is greater than Tsat at 0.7 bar. And so both of those things are going to tell us that it's superheated. We only need one of those to tell us that it's superheated, but I just want to show you that you can prove it to yourself two different ways using table A2 and A3. All right, so let's draw our PV diagram. Bring him up here a little bit. All right. So here we go, and I'm going to draw a little line of constant temperature here. Maybe I'll get it right the first time. I always switch the tails. Sorry about that. So we'll say anywhere along this line, our temperature is 100 degrees Celsius, and we figured that we were superheated, I believe. So let's put a dot out here where it's superheated, and that guy right here would be 0.7 bar. And you can see this guy right here would just be the saturation temperature at 100 degrees Celsius, because if your temperature is 100 degrees Celsius and you're saturated and the water is saturated, you'd have to be at this saturation pressure, which looking up here at table A2, we can see that's 1.014. And right, that makes sense as far as where it's located on that y-axis there. All right, let's do our TV diagram and then we'll move on. Or at least move on to part D, then we'll move on. So temperature, specific volume. Here's my vapor dome. Okay, draw my line of constant pressure here. So anywhere along this dotted line, it's the same pressure. So we'll say that this corresponds to a pressure of 0.7 bar. We figured that we're superheated based on those rules. And so the corresponding temperature, that's 100 degrees Celsius. But this temperature would correspond to the saturation temperature at 0.7 bar, which is something you can get from table A2, or A3, I'm sorry. So at 0.7 bar, you can see that in table A3, your saturation temperature would be 89.95. So let's go ahead and put that here. Perfect. That also sort of goes with our narrative about what phase it's in. Okay. All right. So part D, we've got 50 bar and 20 degrees Celsius. So yeah, let's see what we got here. So first thing that I need to do is I need to go to A2 or A3 and figure things out. I'm going to cross out this A5 because I'm not actually pulling any data off of there. But if I go to A2, I can look things up by temperature. So at 20 degrees Celsius, if it was going to be saturated, my pressure would have to be 0.02339 and we're at 50 bar. So our pressure is greater than the saturation pressure at our temperature of 20 degrees Celsius. So that tells me that it's compressed. Alternatively, we could look in table A3 and see that, okay, well, at 50 bar, if it was going to be saturated, my temperature would have to be 264, and clearly our temperature is less than that. Our temperature is less than the saturation temperature at our pressure of 50 bar. So both of those things would tell us it was compressed. All right, so let's go ahead and get our PV diagram. Get a little line of constant temperature there. All right. So anywhere along that dotted line, we'll say our temperature is 20 degrees Celsius, and I'm going to put us over here. So our pressure would be 50 bar. This one right here would just correspond to the saturation pressure at 20 degrees Celsius, which is table A2, and that would be 0.02339 bar. Clearly not drawn to scale, but okay for our purposes and showing the relationship of that dot where the state is in relation to that dome. And then we could also take care of our TV diagram. So there we go. Draw the line of constant pressure here. Yes. There's our state in the compressed region. Anywhere along here, our pressure is at 50 bar. This is what, 20 degrees Celsius, and this right here would correspond to the saturation temperature at 50 bar, which is over here in table A3. That was 264 degrees Celsius. So we'll go ahead and put that over here as well. So that's the saturation temperature at 50 bar, the only possible temperature that you could be at and be over here in this two-phase region. Okay. So you can use those lines of constant temperature and constant pressure on PV and TV diagrams respectively to figure out what state it is, what state it's in, and justify to yourself, and it's important to be able to do that, but at minimum you need to memorize these rules here, and if you do that, your life will be a lot easier. Okie dokie. So let's keep on going. So problem 12, and once again, just as a reminder, you are more than welcome to interrupt me. Please do if I'm doing something stupid or if you have a question, okay? All right, so we have a piston cylinder device. Contains 2 feet cubed of saturated water vapor at 50 psi. So I've got a drawing of a piston cylinder. I've got the fact that the pressure is 50 psi. They've also given me the volume. They've also told me that it's water. The only thing that I kind of neglected to even write on there was that it's saturated water vapor. So, saturated vapor, that would be something important to note. So what this refers to, and we're going to catch it at the very end of lecture, this actually refers to the quality, and so that's one more intensive property that we will cover by the end of lecture. So at this point, we've got, as far as our intensive properties that we are familiar with and that will help us to fix our state, we've got temperature, pressure, specific volume, and as we'll see, it's something called quality, but this is, do we have a saturated liquid or vapor or some sort of mixture of the two? So those 4 things, just 2 of them, you'll be able to fix your state. Okay. So that's the information that we want to know. We want to know the temperature, we want to know the mass, and we want to draw the location on a PV diagram. So the first thing that I need to do is figure out what tables am I going to, right? What phase is it in? And really the problem has already told us. It's saturated because it's a saturated vapor, right? If we were looking at things on a TV diagram, it's going to be somewhere over here on that saturated vapor line. I just realized I probably shouldn't have. Maybe I'll leave that just in case. I'm sorry, somebody writing that down. All right, so I'm going to my saturated tables because just by the sheer nature of them telling me it's a saturated vapor, I know that those are the tables that are going to give me the properties for water at this state. So I'm going to table A3, which is organized. This is the saturated tables that are organized by pressure. And then also I need to make sure that I'm going to the English unit tables, so the one with an E after it. And at 50 PSI, looks like the only possible temperature that we could be at and be saturated is 281.03 degrees Fahrenheit. So for part A, our temperature, it's TSAT at 50 psi, which is 281.03 degrees Fahrenheit. Perfect. So I'm gonna kind of highlight that so we know. Okay, perfect. All right, then I'm supposed to figure out the mass. So the mass, well, the information that would give me something about the mass is the fact that I have the volume, and I also have an ability to figure out the specific volume, because specific volume, that's defined as volume divided by mass. So my mass is going to be the volume divided by the specific volume. So I have the volume, it's 2 feet cubed. And then the specific volume, well, you could see with my little red line up there, I know it's a saturated vapor, right on that saturated vapor line, because they told me it was. And so any properties that I need are going to have a little subscript G associated with them. So my specific volume is going to be this guy right there. Oh, I'm sorry, this is you. It's going to be this guy. Just kidding. Whoa, that guy. Okay. So it's the specific volume associated with the saturated vapor portion of that two-phase mixture. So perfect. So this is V sub G at 50 psi, which is 8.52 feet cubed per pound mass. You can see I don't really need to do any unit conversions or anything like that. I'm going to get 0.2347 pound mass. Yeah. So that's my mass. And then the very last thing I need to do is draw the location on a PV diagram. So I'm going to do that now. So go. Sometimes it's helpful to draw little lines of constant temperature. I don't really think that's going to help too much in this case, but I know that my state is going to be right there on that saturated vapor line. I also know that my pressure is 50 psi. And I also know that my specific volume is going to be that 8.52 number I got. And I think that's really pretty much it. I mean, maybe for good measure, I put in what this temperature is, 281.03 degrees Fahrenheit. Was that it? Did I need a PV or is it a TV diagram? No, it's a PV. I mean, that's pretty much all the information that I could possibly want about that data point. Okay. All right, so problem 13, we want to know the change in volume, and they actually give us the units there. So when I look at the find over here, I've actually included the units there so I don't forget what units were asked for. So I've got 2-pound mass, and then we're looking at a process from state 1 to state 2. So you'll note that I've got some subscripts there that I'm keeping track of, you know, as far as state 1 versus state 2. And that will be really important to get in the habit of very quickly. Make sure you make a note because, right, state 1 and state 2 are different. So you want to make sure that you're keeping all that straight. So state 1, we start out as a saturated liquid, and it's heated to a saturated vapor. Okay, so saturated liquid, saturated vapor, and it's a constant pressure of 1 psi. And then we want to draw also the process on a TV and a PV diagram. So first things first, I need to, well, really the first thing first is I need to get my governing equation to see what I'm actually after. So I'm after the change in volume, which is what it is after, minus what it is before. And it's really useful to put things in terms of intensive property lists, intensive properties, because that's the stuff that you could pull off the tables. So that's what I'm going to do here. I'm going to put it in terms of mass and specific volume, because specific volume, remember, is one of those properties, those intensive properties that we can use to fix the state. In addition to whether or not it tells us is it a saturated liquid or a saturated vapor. So I'll put over here, you know, quality, which we'll get to, but i.e., is it saturated liquid versus saturated vapor, or some mixture of the two. Okay, so I've got the mass, right? That's given to me, but I do need to figure out V1 and V2. So V1, that's going to be, well, at state 1, it's a saturated liquid, so it's going to be the V sub F at P1. It's the specific volume of the saturated liquid portion of that saturated water, and it's all saturated liquid because they told us that it is. This guy, it's going to be the V sub G value at P1 because it's a saturated vapor and they told us that. Put P2, there we go. So we're at 1 psi. So there's my numbers right there. All right, so I got a V sub F 0.01614 feet cubed per pound mass. This guy is, oopsies, 333.6 feet cubed per pound mass. And so if we're multiplying that by 2, so let's see, 33.6 minus 0.01614 times 2, I got 667.17. 667.17. That is a volume change in feet. Perfect. And then the very last thing we need to do is draw the location of the state, or I'm sorry, we need to draw the process on a TV and a PV diagram. So let's do that now as well. Okay. So for part B, this is going to be our TV diagram. Part C, that'll be our diagram. So let's put this guy like that, this guy a little more that. So I know we're going from, let's see, state 1 is a saturated liquid. Going to be on this side, and state 2 is over here on that side. Same thing for over here. Put a 1, 2, 1, 2. Now over here, it's easy to see why this guy goes in a straight line. It's not 50 psi, 1 psi. it's okay. It's pretty easy to see why it goes in a straight line there, because the line of constant pressure is just going to be straight across. For the TV diagram, maybe it's not so obvious until you remember that those lines of constant temperature, they go like, or lines of constant pressure go like this, right? So this guy is 1 psi, and this temperature right here is the only possible temperature that that water could be at and be saturated, whether it's a saturated liquid or a saturated vapor or some mixture of the two. It's going to be the saturation temperature, which on our table A3E is 101.7, and this is in degrees Fahrenheit. And then the only other thing that would make this diagram complete is to make a note of where V1 and V2 are. And since I've already actually defined what the numerical quantity is of V1 and V2, that's good. But if I hadn't at this point, I would need to make sure that I looked that up and I wrote it, right? V1 is equal to 0.01614, V2 333.6 feet cubed per pound mass. Same thing over here. There's V1. And there's V2. And I also need the process path. Perfect. Okay. I guess the only other thing you might be wondering, like, is there a need to draw that line of constant temperature? I mean, probably fine to not in this case. Really what I'm going to be looking for, I'm going to be looking, do you have the coordinates, right? So on a TV diagram, are you showing T1 and T1 in specific volume? At 1, are you showing T2 and V2 at state 2? Same thing with the PV diagram. Are you showing P1 V1 and P2 V2? Is that clearly labeled? And then also the process path, the location of those dots with respect to the dome, those all need to be there for you to get full credit for a TV or a PV diagram. Okay, so when in doubt, throw some extra information on there to show like over here, I wouldn't have really cared about that line of constant temperature, but it can't hurt to have it on there, I guess. So if you're kind of wondering, yeah. All right. Problem 14, determine the specific volume change. So delta specific volume of water as it undergoes a constant pressure process from a saturated water vapor, perfect, at 100 bar, and this is a constant pressure process, to a final temperature of 360 degrees Fahrenheit. So, and then I also want to put it on a TV diagram. So first things first, got to define what our governing equation is for A, which is pretty simple. That's just going to be what it is after minus what it is before. So I need to fix each of those states. So clearly, state 1 is saturated. And more than that, it's a saturated vapor. So, even though no matter what, even if I didn't know the state of my system, first place I'm going is the saturated tables in the first place. So for state 1, going to the saturated tables. Oh, great, I'm saturated because it tells me so. I'm in the right place. So at 100 bar, my specific volume, actually I'll put it down here where I got a little room. This guy is going to be the V sub G, because this is a saturated vapor, at 100 bar. So it's going to be this guy right there. So this guy is going to be, actually it's fine, right there, 0.01803, and this is going to be meters cubed per kilogram. And then V2, so I know the pressure. and I know the temperature. And that is really all, I need 2 independent intensive properties to fix my state. So I go to my saturated tables, table A3 or table A4, that would be okay. But I happen to be in A3, so I'm going there. So I could see that at 100 bar, I could see that if it were saturated, my temperature would have to be 311.3 degrees Celsius. However, my temperature is above that. So T2 is greater than Tsat at P2. So I know it's superheated. So I need to get out of those tables. And I need to go to the superheated tables. So if I look at table A4 at 100 bar and 360 degrees Celsius, I can see that my specific volume is 0.02331. So perfect, 0.02331. All right, so make sure when you're going back and you're, practicing the problem, make sure you cover this up and make sure you can flip through that PDF. Make sure you can find all these tables. They're labeled for you, right? Table A2, A3, A4. They're labeled for you on the notes, but just make sure that you get enough practice flipping through and finding it yourself and going through that through that song and dance. All right, so we've got enough information to calculate that delta V. So this ends up being, oh good, okay, 0.00528. I mean, that really inspires confidence, doesn't it? It ends up being something. There we go. Beautiful. All right, now we need a TV diagram, so let's take care of that. All right, so just to kind of save room, I'm going to put my units on here. This is in degrees Celsius. Put my dome here. Maybe I draw a little line of constant pressure just for good measure. Help me draw this path because it is a constant pressure process. So anywhere along that line there, our pressure is 100 bar. And then I know at state 1, it was saturated. It was a saturated vapor. So it's going to be right there. That's my state 1. And then state 2 is superheated. We just went through that song and dance. And then the line connecting them goes like this. All right. So in order to get all the credit for this problem, if I hadn't already, I'd need to define what is V1 and V2. But you can see up at the top there, I've already defined what V1 and V2 are, so that's fine. As long as it's somewhere on there, I'm good. The only other thing that I'll need to do here is what's T1 and T2. So T2 is clearly 360 degrees Celsius because it was given to us, but T1 wasn't. However, it's just going to be the saturation temperature at 100 bars, the only possible temperature that the water could be at and be saturated. And so that information we're going to get from table A3. So at 100 bar, our saturation temperature is 311.1 degrees Celsius. So I'm going to go ahead and put that over here. Perfect. And that would give me all the credit for that problem, right? I've labeled the temperature and specific volume for each state. I've clearly drawn the dot for state 1 and state 2 and labeled each of them. I've put those in relationship to that vapor dome, clearly drawn it, and then clearly drawn the correct process path connecting the two. So that would be enough information to get me credit. All right, so we have 12, 13 minutes left. And so I want to introduce this concept of quality, which we've mentioned a couple of times, the relationship to the saturated vapor versus saturated liquid. But this is that fourth property, or fourth intensive property that we're going to become familiar with. So at this point, our intensive property list, and this is always what you want to think, right? When you have a problem, you want to say, which two of these do I know about the state that I'm interested in? So temperature, pressure, specific volume, and quality. Get two of them and fix your state. All right, so quality, we use X for this, and it's defined as the mass of the saturated vapor over the total mass, and it is only defined for regions in the saturated region. So saturation region, only defined for saturated substances. So in that region of saturation, you'll recall that there is a mixture of two phases. You've got a mixture of saturated liquid, liquid that's about to boil, and saturated vapor, which is vapor that's about to condense. So two phases, and so the total mass of those two phases would just be the mass of the saturated liquid plus the mass of your saturated vapor. And if we think of that, what does that really mean? So over here on our TV diagram, you'll see, we have a TV diagram in the vapor dome. Well, over there on the left-hand side, you would have, if it was right on that saturated liquid line, you'd have 100% liquid that was about to boil. And so you wouldn't have any saturated vapor, and so your quality would be 0. If it were on the saturated vapor line, it's vapor, 100% vapor that's about to condense, but it's still 100% vapor. So your quality is 1. So you can see that quality ranges from 0 to 1. It's only defined, once again, for that region of saturation. So something that is superheated, it would be incorrect to say it has a quality. It doesn't, because superheated is, it's superheated. It's not a saturated vapor, it's superheated vapor. It's different. Same thing with compressed, right? A compressed liquid, even though it doesn't have any saturated vapor in there, it doesn't mean that the quality is 0. It would be incorrect to say you have a quality of 0. No, we talk about quality, it's only used to define things in that saturated region. Reason that it's useful is because we know that if that dot, like I have a dot at state 1 on that TV diagram, I know that the specific volume where that dot is the V sub F at that particular temperature. Same thing with state 2. I know that's the V sub G at that particular temperature in my saturated tables. But if I'm somewhere in between, I need a way to calculate that, and that's where your quality comes in. And it's sort of like a weighted average. So this is V sub F plus your quality times V sub G minus V sub F. And sometimes you'll see this written as V sub F G, because with some tables they're nice and they do the math for you and they have a column just for V sub F G. All right, so quality is going to be really useful for calculating properties if you're not right, if you're saturated but you're not right on that saturated liquid or saturated vapor line, but you're somewhere in the middle. All right, next new concept to introduce is interpolation. So we have all these tables with this property data, but it's discrete values, right? And so sometimes you're lucky and your value is right there on that table, but sometimes it's not, and you need to figure out, I need a value between these two values. And so the way that we're going to do that is linear interpolation. All these properties are not they're not typically linearly related to one another. So this is just kind of a section of table A2 where you've got for saturated water, you've got temperature, and then you've got the corresponding saturation pressure. So temperature and pressure in that saturated region, it's not a linear correlation. However, if you zoom in just on like a small little section, then you can approximate the relationship between two little data points as being linear. And Yeah, so that's what we're going to do. So maybe if you look on table A2, you can get a saturation pressure for 15 degrees and 16 degrees, but maybe you need it for 15.2. And it's not as simple as just taking the average of the two, unless you were truly right in the middle. So the way that we do that is we say, okay, well, I know those dots. I'm going to say that, just in that little region, those things are linearly related to one another, or pretty close to. So if that's the case, well, those 3 data points, that means that if I drew a line between those 3 data points, then I could say, well, it's a line connecting them, so the slope between all of those data points has to be the same. And so, well, your slope, right, your slope would be delta y over delta x. So I'm going to arbitrarily call the temperature my x column and the pressure my y column. I could switch those and it doesn't matter. You can organize it however you want. So don't get stressed out about what's x, what's y. It does not matter at all. But if I call this right-hand side my y coordinate, I'm going to work from the bottom up. So just be consistent. Either work from the bottom up always, or you work from the top to the bottom. All right, so what I mean is, all right, so I'm looking at this one, relationship of the slope for this one to this one. Okay, so delta y, 0.01818 minus 0.01705 over 16 minus 15. Well, that's got to be the same as the slope between this guy and this guy. Same thing, working from the bottom to the top. 0.01818 minus Psat at 15.2 degrees Celsius over 16 minus 15.2. And now you're just solving for Psat at 15.2, solving mathematically for that. So I end up getting 0.01728 bar. Okay. And you'll know that you have probably done everything correctly if your pressure ends up being between this guy and this guy, right? If it's outside that range, you probably screwed something up somewhere. You didn't work consistently from the bottom to the top, or vice versa. You weren't consistent. Okay. So make sure you do watch the video on that. Just a couple of examples throughout that, so you can get some practice. Make sure that you actually go to the tables and pull that data. Like, make sure you really follow along, because, well, make sure you really follow along. Extrapolation is kind of the same thing, but instead of looking between 2 data points, you've got two. You maybe have 2 data points here, but you're interested in one kind of outside of it. So table A5, these are the rest, liquid, water tables. And I would actually go to those tables to show you what they look like, show you the problem that maybe we might have. So let's say that we figure, there we are. So we figure that we know it's compressed. We figured that out from the data in the saturated tables. And we want data for 20 degrees Celsius and 20 bar. Now, normally I just go to the pressure, right? However, I do have data for 20 degrees Celsius and 25 bar, and 20 degrees Celsius and 50 bar, but I need it for 20 bar. And so the way that I'm going to do that is I'm going to extrapolate. And you'll notice, if you look back at your notes, I've sort of organized it a little bit differently. I'm going to say, okay, I have data for 20 degrees Celsius, and I have a specific volume at 25 bar and 50 bar, and I need it for 20 bar. So let's go back and look at our notes now, see how we've done that. Okay, so at 20 bar, I've got data for 25 bar 50 bar, and I need it for 20 bar. Okay. And so it's the same mathematical principle, the same mathematical formula. I'm going to say, okay, 0.9995 times 10 to the negative 3 minus 1.0006 times 10 to the negative 3 over 50 minus 25 is equal to, and let's go between these data points now. It doesn't matter, but I'm going to be consistent working from the bottom to the top. So this would be 1.0006 times 10 to the negative 3 minus that specific volume that I'm interested in. Let's color code it just because. Over 25 minus 20. And I would calculate that this guy ends up being 1.00082 times 10 to the negative 3 meters cubed per kilogram. All right, so, you know, as long as you're not like too far outside of that range, then, you know, using linear extrapolation is probably okay. I mean, if you get too far out, then you're probably going to get some more error than you really want. Last thing I want to draw your attention to is these compressed liquid tables in general. There's 1 page of them. And you compare that with the superheated tables where you've got like 4 pages. We do have compressed tables for water in the packet that I've given you, but it's not uncommon not to really have those. In fact, when we look at some of the refrigerants, they don't have those in your book. And so they don't have compressed tables in your book for those refrigerants. And so we make compressed liquid approximations. So instead of, you know, if you figure out that it's compressed, you would say, okay, well, I know it's compressed. However, I know that the specific volume of this compressed substance is really pretty darn close to the V sub F value at T. And so, for example, just kind of going back to this previous problem where we had water at 20 degrees Celsius, like 20 degrees Celsius and 20 bar. Yeah. If I used that approximation, I looked up V sub F at 20 degrees Celsius, I would get something pretty darn close. It's 1.0018 meter times 10 to the negative third meters cubed per kilogram. And this guy is this relationship right here. This is usually the one, you know, if I have compressed liquid tables and my data point just happens to be on them, I'll probably use that. But if it's going to require me to interpolate or extrapolate, I'll probably just use one of those compressed liquid approximations, and it's not going to change things appreciably. Okay, so if you haven't watched those videos, please do make sure that you do. I believe that's the last one. So we will, of course, we don't have class on Monday, but we do have it Wednesday and Friday. So that will be where we'll go over the next 5 or 6 problems, and then you will be ready to come back to campus and do your test. Woohoo! So don't forget, first day back, or first day back in person, you will have a test. So just kind of keep that in mind, okay? Like always, I'll have office hours not Monday, but next Wednesday and Friday, and then your TAs also have office hours, and those office hours are on Canvas, okay? All right, you guys have a wonderful day. Thank you so much, and I'll see you next week. Fingers crossed we get snow. All right, thank you.